Hello, my young scientists. Let's begin with a simple but mind-bending thought. What happens when two mirrors meet at a corner, like the ones you see in elevators or fancy fitting rooms? Ever noticed how suddenly you see yourself from more than one angle? That's not your twin spying on you, that's physics at play. Here's the golden rule: the number of images depends on the angle between the mirrors. The formula is n equals 360 degrees divided by theta minus 1. Now, for perpendicular mirrors, theta is 90 degrees. Plug it in, n equals 360 divided by 90 minus 1, that's 4 minus 1, equal to 3. Boom! Exactly 3 images. So yes, two perpendicular mirrors give you 3 reflections, like 3 versions of you cheering you on. Alright, let's set up the geometry. Imagine two mirrors, ow and ob, standing at right angles, just like two walls meeting in a corner. Place an object P right in between them. The first mirror, OA, gives you image P1. The second mirror, ob, gives you image P2. But here's the fun twist. Each of these images acts as a new object for the other mirror. It's like the mirrors are playing tennis, tossing your reflection back and forth. Let's go step by step to untangle this. Step 1. Object P reflects in mirror ob, giving image P2. Step 2. The same object P reflects in mirror OA, giving image P1. Step 3. Now, P2 acts like a virtual object for OA, producing a new image, P3. Step 4. Similarly, P1 acts as an object for OB, creating P4. But here's the kicker. P3 and P4 overlap, meaning they occupy the same spot. So although mathematically we thought 4, in reality we only see 3 distinct images. It's like when two guests accidentally sit in the same chair, they're counted once. As you can see in the diagram, rays from P strike OB and form image P2. Rays from P strike OA and form P1. Now, the magic begins, rays forming P2 bounce again into OA, giving you P3. Meanwhile, rays forming P1 bounce into OB, aiming to give P4, but overlap perfectly with P3. This overlap is why perpendicular mirrors form exactly 3 distinct images. The ray diagram is like the detective proof. It shows us exactly why math and reality agree here. Now, here's where physics shows off some beautiful geometry. Place the object P anywhere between the mirrors. You'll find that P, P1, P2, and P3 all lie neatly on a circle. The center of this circle is at O, the corner where the two mirrors meet. The radius of the circle is OP, the distance of the object from the corner. So, your reflection isn't just multiplying randomly, it's actually obeying the laws of symmetry and geometry. It's like nature secretly drawing a compass-perfect circle through all the images. Let's solve this in exam style. Given two mirrors at right angle, theta equals 90 degrees. Find the number of images. Model, formula is n equals 360 divided by theta minus 1. Let's call this equation 1. Substitute, put theta equals 90 degrees. So n equals 360 divided by 90 minus 1. That is 4 minus 1 equals 3. Result, the number of distinct images is exactly 3. Notice how both the formula and ray diagram give the same answer. That's physics, consistency between math and experiment. So, what have we discovered today? Two perpendicular mirrors, meeting at 90 degrees, always form 3 images of an object placed between them. Each image is born from reflections bouncing between mirrors, but 2 of them overlap, so we only see 3. All these images, along with the object, lie on a circle centered at the corner point O. This isn't just classroom physics, it's the principle behind makeup mirrors, periscopes, and even clever shop displays. Next time you stand in a corner mirror and spot three of yourself, smile and remember, you've just got physics in the act. And with that, we wrap up today's adventure. I hope you now see how perpendicular mirrors create not just reflections, but a perfect geometry of images. Until next time, keep looking at the world with a physicist's eyes, reflections included.